Okay, so this is lecture 29, and we were looking at power supply rejection regulation in PLLs. So PSRR in PLL. This is what we were looking at. Do you have any questions so far? Okay. So at the very end of the last class, we looked at a regulator with a PMOS as the pass transistor, to which supplies all the current to the VCO. So, and this is V control, or let me just write it as Vref, and this is VDD. Okay. So what we did was we replaced the VCO with a impedance, effective impedance, and that is to find the your actually the transfer functions from VD to V out. So this is RL, Vref, both VDD minus plus, and then you have certain output load cap C out, and you have some cap here C at the amplifier. Okay, so this is V control, and at the end we found that V control by V of VDD. So let me just write it in a small, it's a small signal translation, VDD of S, and this was SVDD divided by so let me just bring it back, the whole one which you can see at the end. Okay, so this was the whole V out by so this is the small signal gain which we found the other day. Okay, let me just write it back there. So I have 1 plus S pi omega out into 1 plus loop gain of the regulator. Okay, this was the case, right? There should not be any problem. Yes. So okay, and loop gain of regulator is A naught into 1 plus S pi omega A into 1 plus S pi omega out, where omega A is 1 over GM of the amplifier times R output of the amplifier, and omega out is 1 over RDS P of the pass transistor in parallel with RL times your C out. Okay. So the magnitude response of this transfer function is, pardon? Omega A is here. Oh, sorry. I wrote 1 by GMR. This is ROA times C of what I wrote, CA. Yeah, sorry. Okay. So mod of V control by VDD is something like this. This one is SVDD by 1 plus loop gain of TC. This is omega A, and somewhere you have omega out. Okay, and the bandwidth for the regulator, which will be you can find that thing by finding Vref to V out as the bandwidth of the regulator. Okay, so okay, now what we do is, so is there any questions so far for this regulation? So you have a peaking response, and one thing, if I want to change the peaking response for any transfer function, can you think of something which I can do to omega A and omega O? Right now I made omega A as dominant, right? I can make omega O also as dominant. And if I make omega O as dominant, what will happen? Actually, omega A comes in 0 also. Omega O doesn't come in 0, right? So you can have, depending on what you have, but depending on which pole is dominant, you can have this becomes omega A, and then you will have somewhere as omega, sorry, this becomes, if blue curve is for when you have this change in the dominant. Okay. Now the only thing is, if you want to make, so let me okay, ask you this thing. So which capacitor do you think, means if you do not add any additional capacitor, will be large, whether it will be CA or CO? CA, right? There's a gate capacitance of the whole big transistor which is supplying the current. Okay, plus it also depends on the output impedance of the amplifier, whereas the effective impedance of the VCO, which is consuming a good amount of current, will be lesser. So in order to make CO dominant, in order to make omega out dominant, you have to have a lot of capacitor, additional capacitor, which you are going to put in the system. So if you want to make omega O dominant, the large area for the capacitor is the trade-off which you will have. Okay, so let's see, this is only the, what we have seen is the transfer function from VDD to V out. Okay, now for, so let me just say I have okay, so ground VDD, and let's say this is regulated, so regulated VCO. So I'm just writing it here as V control of the VCO, and this is V out or F out, whatever. Let me just say, I should not confuse with the terms. Okay, V out here, right? So what we have seen is VDD, the transfer function from from VDD to V control. This is what we have seen. Okay, which is, let me just write it again, SVDD into 1 plus S by omega out times 1 plus loop gain. Okay, now the transfer function from V control to phi out is 2 pi, or if we are writing kVCO in radians, kVCO over S divided by 1 plus loop gain of PLL. There are two loop gains right now which are here. This is for the regulator. So let me difference. Okay. So now, if you look at both the transfer functions, the one which we drew before from VDD to V control is something like this. Okay, do it again. Yeah, yeah, yeah. The supply noise is not that large that your all the system goes out of the steady state. It is some small noise. In the how small, that's always a question. Pardon? Yeah, yeah. No, no, no. So in case of the, so okay, I am writing with whole of the this VCO in the PLL loop. Okay, so do not think that means you have all the phase detector feedback loop is there. So let me just start with other color. Means there is some other block which is PLL. This is there. I am writing the transfer function for the whole loop. I am not writing just for the VCO. PL blocks are here. So this is the transfer function for V control by VDD. Okay. And what can you comment on the phi out by V control? Which one? V out by, we are considering phi out, not V out. Yeah. For regulator, so the thing, okay, what you are saying is right. So let me just do it this way. So if I want that I have not yet considered, that's another step. So if I consider loop gain of ring PLL without regulation, sorry, that is equals to, you have seen ICP by something as S square C1 plus C2. This is for a type 2 PLL which we have seen so far, KVCO into 1 plus S by omega Z and 1 plus S by omega P3. Right, the one which we have RC1, C2 and all those combined. This is without regulation. Okay. Now, when you have regulation, you have another term here, which is, you can say, now this is the V control to V out. V control to, I will just write it. This is V ref to V control transfer function, where your basically your this thing will come. What is the regulation bandwidth, which is very important. Okay. So let me just write your DC gain as 1 for that regulation and S by omega regulation. Okay. So this whole is with regulation. Okay. Now when I am asking you to find V out by V phi out by V control, the loop gain of the ring PLL should consider this additional pole which is coming because of the regulator. But the thing is, the regulator, let's say regulator bandwidth is large enough that it doesn't change things within bandwidth and all. Okay, so given that, what should be the transfer function from V control to phi out? Bandpass transfer function, which is, it again depends on bandwidth. Let's say I have something like this. Okay, let's write it here. Okay, so and where will the peaking occur for this bandpass bandwidth is for the bandpass transfer function is omega bandwidth of the PLL. Whereas the maximum for the V control VDD to V control means, as I showed before, this is omega regulation bandwidth. Okay, so phi out by VDD, because in the end we need to look for the jitter which is coming because of the noise in the supply. Okay, which is now all these transfer functions will multiply. So let me just write them as whatever V control over S by VDD over S times C out. I'm just writing it so that you see that we are multiplying two transfer functions which you are seeing on the left side. And this transfer function is this one is C out by V control. Okay. So the resultant, you can see what the resultant transfer function will be. Okay. Now, okay, the question which I may ask is, what do you think if the picture which I have given you, omega PLL and omega regulation, in order to have a better PSRR, what should be the relation between omega PLL and omega regulator? Pardon? Okay. So for better PSRR, omega regulator should be greater than omega PLL. Okay. That is one case. So let me just point out, there are different things which you can see. Sorry, here. Omega PLL should be lesser than omega regulator. It's both the ways writing the same. So what do you think is the problem here? Or okay, if I want to have a larger omega regulation, what should be the trade-off? Power consumption. So this will actually have large power in regulator. Okay. Which other way you can improve PSRR? What? Okay, so the other one which you are saying, if my this V control to VD in place of that changes to something like this, right? This is a transition you are talking about, where I have omega O as less than omega A for regulator. Okay, this will have large capacitor. But what another thing will happen here means I can have a better PSRR, but if this bandwidth is going to dominate the bandwidth of your PLL now, so that's the problem. You cannot overdo it, right? Lower PLL bandwidth. Okay. Now, in another way means if you lower the PLL bandwidth, what will happen is even this curve will change, right? So you may have something now like this. So this can happen. I mean, these are all the translation which we are looking at. One is we are looking at these two translations, right? Now, if you have a lower PLL bandwidth, what's the trade-off? Synchronization trades. Okay. So you see, means there is surely a trade-off with one design aspect with respect to the other, which is always there. Nothing comes for free. So depending on which block is dominating, you can have an optimum bandwidth, optimum or the best PSRR which you can afford. Okay. So The thing is, initially we wanted to have omega regulator as much larger than omega regulator as larger than omega PLL for stability reason and bandwidth reason. That is one thing, right? But you see, there is other thing. For better PSRR also we need an omega regulator larger than the omega PLL, and that may be dictating more terms for a better PSRR as compared to the stability condition for PLL. So PSRR plays a dominant role here rather than the stability. Once you have said, okay, omega regulation has to be greater than omega PLL, now the question, how much more? 10 times, 20 times, and that will decide your final PSRR. Okay. So we have seen a simple regulator for a ring oscillator, but there are other techniques in which you can improve PSRR. So let's look at them. Any questions so far? I mean, this is a very simple regulator which we have seen. Okay. So the first one is you can in place. So we have used a PMOS as a PMOS as a current source. We can use NMOS transistor as current source, and which we have seen NMOS transistor actually gives you a better PSRR from VDD to V control of the VCO. Okay. So let's see that and VDD. So I'm just trying a simpler first one. We can try more complicated other time. Okay. RF and CF. This one is VDD. And this is V control. Okay. So in this case, so let me just write this as Vx node. You see that Vx is actually the filtered of the VDD. To begin with, the way I have used it, that the control voltage for the VCO is gate control is VDD itself. DC voltage VDD itself means you can put a source follower in between and then you can change the control voltage with a certain VDEF. But right now, let's assume only this is a simpler case. Okay, so here you have Vx over VDD as 1 by S CF RF. First question. Resistance means what? No. I'm just conceding a simple one. Right now, just concede. So, okay, let me tell you this. So here, in this, that's what I'm saying. If you are not using any complicated low dropout regulator, this is the simplest one which you can use it for PSR. Okay. So if you consider in this case, right, at the low frequency, you can see where the gate and the drain are the same voltage. Sorry, gate and the drain are the same, right? Whereas at a high frequency, your gate is roughly shorted. So when the gate is roughly shorted, if you recall what we had with when we were trying to use an NMOS as an output stage, where gate was roughly shorted, then VDD to V control was 1 over GMRDS1, right? So if in the case of the PSRR which we have seen, means I would say at relatively larger frequency you are seeing a peaking, right? Whereas if we do something like this, where the gate becomes shorted at a higher frequency and VDD to V control is actually 1 over GMRDS1. Huh? No. So, okay. The case which we considered was this. This is VDD. In one case, we coupled directly to VDD. In other case, what we did, we have and we make it to ground. Okay, I didn't say how are we making it to ground. So I'm saying that at a very high frequency, you can consider that this gate is actually effectively shorted to ground. And if it is shorted to ground, then what is the output? It's 1 over GMRDS1, right? So means that so looking at the previous PSRR curve where we see that at a medium to high range of the frequency, it is having a peaking in the system. You can think that I need something to reduce the high frequency peaking. Okay, so for this, sorry, I think you can work out this transfer function. So this is with respect to omega. Okay. This one is V control with VDD for the transfer function which you are seeing there. So this is 1 over GM RDS of the NMOS transistor. Okay. And this is your omega F, where omega F is equals to 1 over CF RF. Yeah. Low filter output of the PLL directly to BDEF. Yes. Yeah, we are not still talking about that. So the thing is, okay, this is the simplest way to see that I can control RFC. I can control the gate of the, yeah. So the thing is, we will now, if we want to increase, make it better, we will then have the source follower and then control it. But the thing is, as soon as you start having source follower, it gets a little bit complicated. So I started with the more simpler one. And there is another thing. In case, okay, if you control VDD directly, let me just put it that way. Okay, VDD can be controlled as per V control. So let's say if I do not want to change this part, then where should the loop filter output will connect to? To VDD, right? Because the control voltage which is being passed to the oscillator is directly related to VDD here. Okay, I mean, this is just to do a simpler one. Okay, so now, so this is the translation from from VDD to V control, and what we have is again I am looking for the translation from V control to V to Phi out, which is something like this, where your PLL bandwidth is omega PLL. Now the combined will be the combined of these two, means the Phi out to Phi out with VDD. So what relation should be there for omega F and omega PLL for a better PSRR? Pardon? Omega Fs has to be low in this case. For better PSRR, you need to have omega F much lesser than omega PL. Okay. So if you want to think it simply, you think it this way, that here I am going to control VDD with my whatever my loop filter output is with some buffer which can give all the current and everything, and that voltage is just coming as VDD. Okay. If we want to use the NMOS directly, V control coming into an amplifier controlling this NMOS, then we can use this one. Then you need to see what happens. Means I'm not going to talk about this. So this is your Vref coming from the loop filter, and this is your V control. can work out this how it changes the time. Okay. Means you can say what we have seen, what I have done is I just remove this part completely. Okay. And just did a simple one. Difference which you would like to see here is that in this way you are actually getting a suppression at a higher frequency, no peaking in the response. Okay. And but you see that at low frequency you are getting a gain. So looking at in one case in the previous regulator, you see that I am getting a lot of or a lesser gain at a lower frequency, but a peaking at a higher frequency. And here I am having a suppression at a higher frequency, but a finite or a larger gain at a DC. If I want to have both DC and high frequency benefits, what shall I try? Okay, so let me see. So what you are saying is, let me just draw it and then, so I have, this is the one which gives me control from, let me just mark it, this as V out 1. This one gives me control from VDD to V out 1, which is having the transfer function where you are getting a high frequency suppression, right? Now what shall I do with this? So if I, let me, sorry, here. So I suppress the supply noise at a higher frequency using the NMOS regulator. And so what did I do? If I, same node as, so I have something here. This one is V out 1 by VDD. Okay. And V out 2 by VDD is something like this. This is, sorry, V out 2 by V out 1. Okay. So now you can see there might be something in between, depending on where the 0 or your gains are. You can have, you see, it all depends on the gain where your axis are lying. You can have something like this. It all depends on which pole and frequency is coming. So I'm not drawing it to exactly scale. I'm just showing you what the tentative will look like. So this will be something as phi out by VDD. Huh? Yeah, it is gone. So that's the trade-off. So you get a regulation, but bad part of this is that larger headroom. For regulator. Okay. Means you can try something with a different bandwidth at different regulators. So this normally comes in cascaded regulators as to improve PSRR. So as many regulators you know, you can think if the cascading if is giving you any better, any benefit. Trade-off will surely be there in terms of headrooms if you are cascading in this manner. Okay. So just for your information that uh, the NMOS which you are going to use for the top regulator, right? So if you are using the same NMOS which you use, so okay, let me just check. In any given technology, just pick up any, you have in a given CMOS technology, you have different kinds of devices, right? One is you have regular VT, okay, low VT, high VT, okay. Which other device have I left? Huh? Zero threshold voltage. They are normally called as native devices in a given time. So see, if I am going to use the same regular VT everywhere, then I need to have that threshold voltage and overdrive drop, right? Whereas if I go and use a native devices for just for the NMOS, I can have a regulation. But it doesn't come for free. Native devices come with a good amount of leakage current and a lower RDS values. So those things are there. But you can surely, if you want to do it, you can surely try it. Yeah, if you do not want a very specific PSRR, but good enough, you can try native devices. These things work. Okay, so that was another way to improve PSRR, and there is so let's look at this one, right? The one which I have said that I can always have this V control to VDD conversion, which I have shown you here. Sorry, this one, right? This conversion, and this is actually coming with the problem of that I have a PLL bandwidth issues. Then it will come if I make that dominant. So what what we need to do is we need to have the dominant pole at the output of the regulator, right? At the same time, what we are having is we want to control the VCO, which is having a different this thing, which is having like so okay. So one thing which we first thing which we want is we want to have a dominant pole at the output of the regulator to control VDD. Sorry, to control the current source in the oscillator. Okay, but we do not want to use a larger capacitor. Okay, also we want to have a like this should not be a constraint on the PLL bandwidth itself. Okay, so there are different things. A larger capacitor is a problem if you want to use it at the uh, with the regulator output only. The other thing is that as you change your frequency of the oscillator, if your output pole is the dominant pole, right, then that frequency will vary, so your effective resistance of the oscillator, and so your pole will move. Okay, so we do not want to do that too either. Okay, so for that there is another one which is called as a replica biased low dropout regulator. So this works on the fact that, so let me start the other way, that I have a current source to my oscillator where the frequency will vary, so the effective resistance will vary. So let's say this is final V control. What I do is I create a replica of that R replica of the VCO. So C out and say C. Okay. And this one is Vref. Call and any capacitor will come here. Let me just make it as this as a replica one. So C, this should not be replica. This is something as a parasitic cap, which you can have. Okay. So let me ask you this. So earlier in the previous case, if you see what we had this was the earlier case, Vref, VDD, right? So means these two transistors effectively do not change, right? If I am running the oscillator at the same frequency. These two transistors do not change, so effectively the load at CA, capacitive load at CA, if the replica is much smaller version of the output main current source. So this is M replica and this is main current source. The replica is normally much smaller than the main current source, so your CA will not change that much. What is coming with the parasitics? The additional you put, that's a different case, right? Now, in case what the regulator on the right side, you have a smaller resistance. Let me just call this as effective RVCO. This was a small resistance, and in order to make this pole as a dominant pole, I have to put a larger cap to make it dominant. Right? Now here, if I'm using this replica, this is something as, let's say, n times large, right? Surely your MR has also gone, MR size should also go down. So this will be, if this is something as W by L, this is, okay, let me write this as W by L and this is N times W by L. So now using this, you are not constrained first thing with the larger cap to have a dominant pole, output pole as a dominant pole in the regulator. The right side has nothing to do with the regulation right now. Okay. So it will be easier for you to get means you have to work out all this expression. So let me just say this node, this is Vx. So from VDD from VDD to, okay, you can get this as V out 1. So this is V out 1 by VDD. You can get this transfer function with the output pole as a dominant pole. Okay. The thing which you need to find is Vx by VDD. Okay, and then V out transfer function. So this I will left you to work this out, that the effective transfer function from VDD to V control is something, let me just use a different, don't go for the scale here right now. So you can have with the replica base. This will be V control by VDD. So what does it rely on between MR and MM? Means The thing is, the regulation of the current which we are doing on the replica, we assume that that is exactly replicated on the mm. So mismatch between mm and mr. So mismatch is a problem. mr and mm degrade PSRR. Okay. So any questions? So the other thing is that now I am using a VCO as a real load. If I want to use a replica of the VCO, what shall I use? Pardon? No, right? Okay, so so let me just put it this way. Whatever, so the one way is, let me just say, the two VCO means if you are using a replica VCO, the two VCOs cannot run at different frequency if you want a real replica of the VCO. So here, if this VCO is of size W by L in the replica, right? So this is main VCO and replica. This is, let me just scale this so that then talk. So in a replica VCO, I reduce each inverter size with by n factor, but they are still operating with the same supply. You see the V out one and V control at DC, they have to be same. Otherwise, I do not have any regulation proper, right? So if that is the case, then the other replica VCO will also run at the same frequency. That is not changing. The only thing is means the one which is running at with a lesser amount of current is actually will have a more phase noise, but that is not what we are looking at. So you can always have the replica VCO. The problem with the replica VCO is that the current which the replica VCO is consuming will be a switched current. So there will be a lot of glitches supplying here, which are actually there in real VCO. You suppress it with the capacitor. V control cap is not necessary. No. Area is so that okay. Let me just put it this way. The capacitor at V control, you will put that capacitor at V control not for regulation or anything right now. The capacitor V control you are going to put for basically suppressing any ripples if you are seeing it there. I mean the regulation has already been done. So the thing is, if let's say if the VCO size is n times smaller, so if you think that this capacitor's okay, if the VCO scaling factor is going by n, then the capacitor scaling should also go by n. No, that's not. I will not do that part. Means otherwise, if the capacitor also scales by n, that means I am already using a large capacitor on my VCO. Okay. Pardon? So the replica regulator regulates Vx, and from Vx only it is regulating your V control. Yeah. That another pole will come. So that would be a good one to work out the whole expression. What it is V out by V reference. Okay. So Okay, coming back, we were talking about the replica. I think we have to stop here. We'll continue tomorrow. People are waiting outside.